So, in this video we're going to talk about a bit of a topic where maths, chemistry and physics kind of overlap, in particular where some of the theory in A-level maths can be used to work out some of the equations in A-level physics and a bit beyond in chemistry, but it still uses some of the context. Now, I really want to put this out there because it's a topic where it becomes really useful if you study the subjects together. It's about connections, it's about where they're useful, and that's really where you can develop knowledge, where those topics overlap and you have a better understanding of one because of the other. So we're going to look at two topics in science. We're going to look at nuclear decay and we're going to look at first order reactions in chemistry. We're going to look at those through the lens of differential equations in maths. So we'll be able to derive and understand some equations a bit better because of what you may have learnt in A-level maths. So we'll start off thinking about decay, particular nuclear decay. Think about nuclear fission. Think about nuclear fission reactions. The nuclei collide with each other. Get something like uranium-235, gets some neutrons, uranium-236. That gets unstable, decays into two smaller particles. They then collide with others, destabilize them, they decay, become more particles. We're going to think about the decay rate. So that means we're going to have to be keeping track of the number of nuclei, which I'm going to call n. Okay, and obviously we'll use t to call the time. Now, if we want to think about the rate of nuclear decay, it's the change of the number of nuclei over the change in time. Well, to get it at any particular instant in time, I'm going to talk about dm by dt, the derivative of whatever n is with respect to t. Now, there are all sorts of different ways of modelling nuclear decay, so this is just a particular example of how one might do so, but it's used at A-level physics. And it's that we're going to say that this is proportional to the number of nuclei. Okay, so that means it's going to be a constant, which we call lambda. And if we think about it, we've got more nuclei, we're going to have more decay happening. We get less nuclei, it's got less decay because the particles not colliding with each other. An important thing is the number of nuclei is decreasing, so I'm going to put a minus there to show that the number of nuclei is going down with respect to time. Because lambda is going to be a positive constant, and number of nuclei, that's got to be positive. So we've got a differential equation now modelling nuclear decay. Let's try and think about how we can solve this differential equation using certain techniques from maths, and then how we can apply that to get some useful results in physics. So if you're an A-level mathematician, you might want this equation is a little bit like something, well, so you've got the exact same structure as something like this. So think about how you might solve that, and think about how you might apply that to this. In particular, we've got n's on both sides. We need to get the n on one side, so we can actually use it. So I'm going to have 1 over n dn by dt is equal to minus lambda n. Now if I integrate both sides with respect to t, get this. Sorry, I've divided by n, so no, that's still there. So the left side of this might look a bit messy. You might be tempted to cancel off the dt's. In A-level maths, probably like times by dt. That's not something that really you can do. Different derivatives like that are not fractions. It's more the notation is very clever because you can get the right answer by thinking through that way. So if you want to do that for A-level, that's fine, but if you go to any university courses, you can't do so because you start thinking about partial derivatives, where that sort of trick doesn't work. So this is really because of the integration by substitution formula. So I can change my variable integration as long as I've got the derivative in there. So what it reduces to is this. But you can see I could get a bit quicker just by quote unquote times by dt divided by n and integrating that original equation. Now the integral of 1 over n is going to be log n, it's natural log base e. Integral minus lambda, it's going to be minus lambda t, and we've got an indefinite integral, so it's going to be plus c. Now to rearrange it for n, the opposite of log, or ln in particular, is e. over e to the minus lambda t plus c. Now I'm going to write this in the so I'm going to write this as e to the c times e to the minus lambda t, and e to the c is just a constant, so I'm just going to call it a for now. A e to the minus lambda t, where a is just a constant, as e to the c would be. Now, I think about more of a convention. So if we call the number of nuclei at start n0, i.e. when time is 0, the number of nuclei, I'm going to call it n0. Put this into this equation. So replace n with n0, replace t with 0, remember a e to the 0, the words n0 is equal to a, and e to the 0 is 1. My equation becomes n equal to n0 e to the minus lambda t. And physicists will recognise this as the decay rate equation, the nuclear decay equation that I've got. And that tells us the number of nuclei at any point if we know the starting number and we know this constant, which we call lambda, the decay constant, which kind of represents the probability, divided by n, kind of represents the probability of nuclear decay in a small time interval. So that's one equation that we can get. We can use that to model nuclear decay and compare it with the experiment. Another thing that we can think about is half-life. So let's actually give a mathematical definition to half-life. It's the time taken for the initial number of nuclei to half. So when t is equal to half-life, which we tend to represent as t a half, that means the number of nuclei is equal to half the starting. Okay, so that's what half-life means, literally. Not half-life, but half our starting value. That's what this says, just in algebra. So let's put this into our equation. Place n with a half n naught. So I've got a half n naught equal to n naught e to the minus lambda t a half. So the half-life, it's not t times a half, it's t subscript a half. Now I can divide both sides by n naught, so they're going to cancel. Opposite of doing e is log. So I have log of a half minus lambda t a half. Now log a half is the same as log of 2 to the minus 1. 2 to the minus 1 is a half. And our rules of logs tell us that that minus 1 comes to the front power. So actually this side is the same as minus log 2. So log a half and minus log 2 are equal. I don't get that. Cancel out the minuses and divide by lambda. Log 2 over lambda is equal to half-life. Another equation that physicists will recognise. So that's an example. You can do a very similar thing with the activity of nuclei, so it's worth trying to do that using this as an example. This is an example of where we've taken some A-level maths and calculus, applied it to A-level physics, and we've got our equations that we use quite frequently in A-level physics. And I want to talk about another example, which is, well, it's going to be very, very similar, which is going to be kinetics, chemical reaction kinetics. So kinetics is all to do with the rates of a reaction. Chemists and much you're thinking about, we've got thermodynamics as well, that's all got to do how feasible a reaction is, how does the reaction happen. Kinetics to do with how quickly the reaction happens. In particular, let's have a look at a first order reaction. So a first order reaction, and where all the powers are up to 1, so you could say that the rate is equal to K times your reactant, which we're going to call A, and square brackets means concentration of. Okay, so concentration of A. So the more particles that we've got, the quicker the rate's going to occur. That's what first order reaction is. Let's think about how we could assign a meaning to this rate. Rate be dA by dt. And because it's decreasing, we're going to think about particles. The reaction is going to be A going into something. So I'm going to say this is minus K times A, without a disappearance of A. Now I just want you to first of all take a little look at that, then think about how similar it is to this equation at the start of the previous one, which I'll just flash back to. The dn by dt is minus lambda m. Here we've got dA by dt is minus Ka. Very, very similar structure equation. So I'm going to sort of, I'll do the cheating way for this one. So let's times by dt, although not really, and let's divide by 1 over a dA, and then integrate. Okay, so that's the quick way of doing it. 1 over a integrates to ln a, and I've got minus kt plus c. To rearrange it for a, I've got e to the minus kt c. Okay, so we have a is e to the c, e to the minus kt. And I'm not going to call e to the c a to confuse the reactant, so I'm just going to call it b temporarily, just so I don't confuse it with the reactant a. Now let's do a similar thing to before. Let's say at time 0, the concentration is the initial concentration, E0, is the initial concentration. So I'd have A0, put it into that equation, is B, e to the 0, which is 1, B0 is B. And therefore our equation becomes A, concentration of A, equal to the initial concentration, e to the minus kt. That's our equation for a first order kinetics reaction, which is sometimes we might say that the nuclear model that we just used was a first order one, because it's governed by the same equations. It might have different symbols in them, but they've got the exact same structure. We can also do something with the half-life, so you can say at the half-life, concentration of A is half its initial concentration. Put that in, so I've got half A0 is equal to A0 e to the minus kt a half. Cancel out A0, take logs. Log a half, which we said before is minus log 2. Going minus kt a half. I'd get that kt a half is equal to log 2 over k. Right, so that's our equation for a half-life. The amount are very, very similar. Now, another thing to note in particular is that the first order reaction, the half-life, is constant. Now, that's a really important thing for chemists to know to be able to identify a reaction, the order of a reaction, if you've got a constant half-life. Why is it constant? Well, it just depends on the rate constant. So it only depends on the temperature. Okay, nothing else. So that's why it's constant at a particular temperature. So we've got the T half is constant. Let's compare it maybe with one that might not be constant. So let's look at a second order reaction, where we've got the rate, I'm going to say just for this case, is going to be a single reactant like that. So we have 2 lots of A in our rate determining step becoming something else. So let's have a think about what's going to happen now. So again, label it. Rate is going to be dA by dt. Going minus to talk about disappearance, Ka squared. Let's rearrange. We're going to divide by a squared. Times by dt, which again isn't correct, which I'll just say every time, but it works. And then I'm going to integrate. Integral 1 over a squared minus 1 over a, and that's minus kt plus c. Let's do our condition when t is 0. A is going to equal A0. So I have minus 1 over A0. Let's put 0, so is equal to C. So our equation becomes minus 1 over A is minus KT minus 1 over A0. Now I'm going to rearrange it a bit, so if I add 1 over A0 to both sides, and this equation. Okay, and I could even get rid of the minuses, flip this side. And put KT like that. However, it might make more sense to keep it as it is, because A0 is going to be a smaller number than A. So 1 over A0 is going to be a bigger number, so this side will be, yeah, let's take that. Right, so we can then also think about when t is t a half, we would have A is equal to A0. Right, half A0. Let's put that into our equation. So I've got 1 over A0 minus, I'd have 1 over half, which is the same as 2 over that thing, is equal to minus KT. Some of you might be able to show that bit, so let me just show that. So 1 over a half A, so that's likely to be 1 divided by half A. Now remember that we can times and we'd flip it. This thing is A over 2. That becomes 2 over A. 2 over A like that. Not over. So 1 over A0 minus 2 over A0 minus 1 over A0. And that's equal to minus KT a half. Get rid of the minuses, divide by K. T a half 1 over A0 times K. Right, now that's not constant. Depends on your initial concentration. Okay, so that's a not constant one, so that's how we know that a second order reaction doesn't have a constant half-life. Okay, if this equation varies unsatisfying, I kind of don't blame you. You could rearrange it to get what A actually is. You can do it at the bottom. So get rid of all the minuses for starters. I'd have KT plus that. Now let's get it all as a common denominator. So cross multiply. So I'd have KT A0 plus 1. That would be equal 1 over A. So if I wanted what A would be, I just need to flip it. So A would equal A0 over KT A0 plus 1. That would be the second order rate equation for the actual concentration. So it would be a concentration equation, I guess. But that's showing how, in the previous example, we had constant half-life, first order kinetics, as we did for the nuclear decay. And then for a second order chemical reaction, it's shown here that it depends on that initial concentration. So it's not got a constant half-life, and that's a way of identifying the equation will look like. So I hope this sort of illustrates to you the power of using maths, in particular calculus, to model things in science. You could use it in biology for population growth. When you study mathematical biology at university, they offer lots of courses where you can study these things in more depth. But it's just an example where, using a bit of available maths, you can derive some quite useful equations in the sciences. So I hope you found that interesting, and thank you for your time.